Today is our great pleasure to have Professor Alex Cloninger to here to give a talk. So Alex received his PhD in applied mathematics from University of Maryland. Then he was a postdoc and a Gibbs assistant professor of mathematics at Yale University. He's now a assistant professor in UC San Diego in mathematics department. And Alex research in area of the geometric data analysis, applied harmonic analysis, and he focused on approaches that model data being locally lower dimensional, including data concentrated near manifold and subspace. And this type of problem raised in a number of scientific disciplines, including imaging, medicine, artificial intelligence, and the techniques developed related to a number of the machine learning and statistic algorithms, including deep learning and network analysis, and so on. Yeah, without further ado, so let's welcome Alex. His title today is Operating Invariance to reduce the complexity of the parametric linears. So Alex, I give you the open go.
Awesome. So there for a moment, things froze. So internet being slow, if it is.
Oops.
Incorporating those invariances to really reduce the complexity of a parametric learning algorithm. So this is work. I'm going to start talking about two main problems. One is work with Timo Klock, and another is work with Caroline Moosmueller. Both are postdocs. Timo's sort of half-time here. Caroline's a postdoc here at UCSD in the math department. And I will note both will be on the assistant professor job market soon. So I'm just sort of advertising on behalf of them to keep an eye out. I think Caroline will be next year, Timo maybe slightly next year, and then mostly the year after that. So acknowledge some funding, all that. Okay, so what am I talking about when I say incorporating invariances? So basic setting, we're trying to learn a parametric function to approximate some target function f that maps from data into the real numbers, into a class, whatever. So the issue obviously is that when you're in a high dimensional space, you need far too many parameters, right? The number of data points is going to need to, you generally need a number of data points to exceed the number of parameters. Number of parameters is going to be huge when you're in a high dimensional space. This just becomes all kinds of problematic, right? So what's a way that we can approach this in a little bit more, realistic way? Well, one way you can sort of find a partial solution is to incorporate a priori information about your problem to really reduce the dimensionality. And the way that I'm going to talk about it is through the concept of invariances. So for example, maybe by incorporating the fact that my function that I'm trying to learn, I know it has to be translation invariant. I can reduce the number of parameters needed. Or invariant to some sort of group action. Or invariant to, say, projection onto a low-dimensional manifold, a low-dimensional space, right? So all of these invariances we're going to start to talk about. And the question is, how do we actually use these invariances to reduce the complexity of our parametric model? Okay. So I'm going to talk about two examples, and these examples are a little bit disconnected from each other. So basically, I'll spend the first half on deep learning, and the second half I'm going to talk about optimal transport. Both there's sort of some relevant stuff, some connections. But the first question I'm going to talk about is basically, can we approximate some function with a neural network where the complexity of the neural network is actually able to go beyond the intrinsic dimensionality of the data? Okay, so the setting here is you have data set, it's in RD. We could assume that data set is concentrated on a lower dimensional manifold, near a lower dimensional manifold, things like this. And we're going to assume that our function is actually invariant to movement off the manifold. Okay, so that's like invariant to noise off the manifold, invariant to group actions or something like this, right? And the question will be, how many parameters do we need to work in this setting, right? And the other question we're going to look at is going to be related to doing supervised learning in a slightly different way. We're going to actually be talking about supervised learning not on a point cloud, but on a cloud of distributions. So every training point, every point is going to be a distribution, and a distribution gets a label, right? And we're going to say, all right, well, first off, there are a lot of problems here. How do you even do learning on distributions? We'll talk about that. But in particular, what if I assume that I need my function to be invariant to group actions? Like shifting the distribution should not affect my classification. Rotating, scaling my distribution, none of these things should affect my label of the distribution, right? So we'll talk about this as well, and this shows up in a lot of contexts, from some medical data that I work on to, you can think about images as being densities on R2, and we're going to talk about building in, transformation invariants of various types. So that's the basic idea. I'm going to go ahead and jump into the first topic. I should have said, if you have any questions, please feel free to unmute and let me know. I'm happy to take questions whenever. All right, so first problem we're going to talk about is what we'll call the manifold projection model. Okay, so this is related to deep learning, and real quick, I'm just going to do like a 2-second overview of deep learning. I promise I'll be fast, but I'll overview it from the approximation theory perspective that I'm taking, right? So when I say deep neural network, what do I mean? You've probably seen an equivalent of this slide a million times. Right? I just mean a feed-forward network where you take your point, you multiply by some affine transformation, nonlinearity, affine transformation, nonlinearity, so on, so on, so on, so on. And our goal is to estimate the marginal distribution of the expected value of the label given the data point, right? And we design our architecture, and then you try to solve with stochastic gradient descent or something like this, right? So independent of networks, there's this problem of the curse of dimensionality. Okay, so for any learner, there's this idea of like empirical risk minimization, which basically says that if you're in a truly d-dimensional space and you're trying to learn like Hölder functions, then the best you can do in terms of the number of points, n, is going to be an error that decreases with a rate that depends exponentially, that depends on the ambient dimension. There's really no way that you can beat this, right? And then a way to reduce that a little bit and to incorporate an additional prior would be to say, oh, I'm going to assume that my data is concentrated on some k-dimensional manifold, or some, there's some k-dimensional subspace that splits up my classes or something like that. And in that rate, again, this is independent of networks. This is just some statistics, this is just some, risk minimization statistics. You could actually reduce all of the complexity down to the intrinsic dimension of your data. The number of points you need is going to scale with the intrinsic dimension as opposed to the ambient dimension, right? So this is the setting we're in, right? And there's always a bunch of discussions about approximation theory and deep networks. And the first famous thing was like Sabengo and Barron. And they basically said, if your function is continuous, you can always, approximate the function with a neural network, with no real discussion of how complex the network has to be, right? So what we're going to talk about is actually trying to say how complicated the network has to be in order to approximate certain types of functions. And by complicated, what I'm going to say is that it's actually going to be related to the depth of my network and the number of non-zero parameters in my network. Okay, and the reason that these two things are really critical is because what we have here is basically the if you're dealing with, say, Hölder functions, or really any types of functions, and you want to cover that with some finite collection of possible sort of candidate functions so that you're not searching over an infinite dimensional space, how many do you need so that any candidate function is sort of within delta of the ground truth, right? Well, that's going to scale basically with the depth and the number of parameters. And so the thing is that the depth and the number of parameters really are sort of a measure of the complexity of your network. Okay, how many functions can you learn? How complicated of a function can you learn? Okay. So that's the idea, but what we really want to do is tie that in not just to approximating functions, but we also want to tie it into how good our approximation is actually going to be, right? So we want to talk about how our depth needs to scale with the class of the function we're trying to approximate and with how well we want to approximate it, okay? So that's basically going to be the setting, is can we bound the sufficient depth and the sufficient number of parameters so that we can learn certain types of functions. And then all of the number of points needed actually just kind of comes freely from that using sort of standard empirical risk minimization techniques. Okay, so there's a couple of papers that I'm just going to highlight here. One there's a famous paper by Uratsky a few years ago, Schmidt-Huber, basically said that if you have a Hölder function in RD, or in the unit interval, the hypercube in D dimensions, you can always find a rectified linear unit network from the class of networks with basically log 1 over epsilon depth and epsilon to the minus ambient dimension over alpha. Number of parameters. You can always find a network such that it pointwise approximates the true function within epsilon. This is about optimal, and I should note this has a cursive dimensionality, right? In this case, if we're really assuming that the data comes from the unit cube in RD, this is the best you can do, and we're only assuming that the function is ordered. Okay. There are other results. So one of which is mine from a while ago. Schmidt-Huber proved a similar type result that basically says that for what I'm going to call a nice manifold, so an actual manifold, right, which is locally k-dimensional everywhere. So it has a k-dimensional tangent plane everywhere. Nice, I mean smooth, regular, satisfies all the bounded, satisfies all the assumptions you need. If you're trying to learn functions that are Hölder on that manifold, then the complexity of your network doesn't actually have to scale with the ambient dimension. It only has to scale with the intrinsic dimension. Okay, which is nice because what we're doing is we're saying, all right, what if we had a quote unquote? In some sense, you're saying, what if you had an easier problem, right? You're saying, what if I reduced the number of functions I have to think about, right? But in reality, it's actually a harder problem to learn functions on a manifold, because then you have to worry about things like the reach of the manifold, the curvature of the manifold, all of these complicated aspects, right? But by doing that, what you wind up getting is that you can reduce the complexity of the network needed down to intrinsic dimension, some polynomial dependence on the ambient dimension. All of these methods basically depend on building a manifold atlas and then a partition of unity. So that's basically building a covering charts of your manifold and then some partition of unity on it. And I should say this isn't special to deep learning. There are a lot of different things that can reach intrinsic rates, right? Radial basis functions, for example, if you're doing any sort of kernel density estimate or kernel regression. Okay, so that's a quick overview of deep learning and approximation theory. What is the model I want to think about? So I want to think about things that aren't nice. So one version of that is that real-world data is messy due to noise corruption, right? So you can't always assume you have a quote-unquote nice, smooth manifold. You might have a noisy manifold in which you have data that sort of, it's concentrated near a low-dimensional manifold, but not on it. There's a lot of noise in various directions and various sizes, okay? So in that case, the way to think about it is that the function we're trying to learn does not depend on the coordinates of the point. It actually depends on the coordinates of the point projected onto the manifold. Okay, and in this case, I'm defining the clean sample projection onto the manifold as the closest point to the noisy point where that point does lie on the manifold. Okay, so if I'm assuming that I have a function that, if I'm really calling these things noise, these little deviations, I'm implicitly saying that my function is invariant to that noise and only depends on where it is on the clean manifold, right? And so this motivates analysis of these types of functions, where f of x is really g projected onto a manifold, g of x projected onto a manifold. Okay, that's one example. I want to talk about another version of invariance, which is what happens if your real-world data actually has symmetries. So again, we could have a manifold hypothesis, or you could actually assume that your function depended on a number of parameters that's even smaller than the intrinsic dimension of your manifold. So for example, we have these images and we're assuming that they lie on some manifold. I know it's sort of disingenuous necessarily to say that MNIST lies on a manifold. We can talk about that later, but for any manifold type assumption, right? You could say it lives in some little d-dimensional space, but there are additional invariances in our function. Like our function should not depend on rotation of the image, right? It should be a classifier that doesn't really care that, any point on this orange curve is going to get classified the same way. That's an assumption of invariance of our function, right? And it's the same thing as basically saying that we're assuming that we want to basically say that our function only depends on the projection onto something invariant to our group action. So that would be like saying that we want to pick some z such that it's close to x, where z is on our original manifold, where x is our sample pushed forward with some group action. Okay, sorry, I realized I should have had the group action element in there, but that's fine. But my point is that both of these are here to motivate that we want to think about functions that can really be written as a function of x projected onto a manifold. And the key is that I don't necessarily assume my manifold I'm talking about is the data manifold. It could actually be a very, very, very low dimensional object. I could have data that's concentrated in high dimensional space, but assume that my function just is about where x projects onto some line in that high dimensional space, right? Then my manifold is dimension 1. Okay, so this manifold could very much be much lower dimensional than even the intrinsic dimension of the data. Okay. So I want to comment real quick about what is an admissible domain, like what type, when can I apply all of this? And all of it is basically related to what's called the reach of the manifold. If you're familiar with some differential geometry, you might be very familiar with reach. If not, I'll give you like a 2-second non-technical explanation. The reach of a manifold is basically the largest distance such that the projection is unique. So basically, how far can you move off the manifold and still have a unique projection back onto the manifold? Okay, so obviously x does not have a unique projection onto the manifold because it's equidistant from all of these points. But anything outside of a tiny little ball around x does have a unique projection onto the manifold. Okay, so in that case, we define the reach to be the distance to what's called the median of the manifold. And our assumption is basically going to be that our domain is some tube of radius q times the reach around our nice manifold. Okay, so basically, we're just saying that we're assuming our function is going to be able to be written as a function of data on that manifold. And the domain is a tube around that manifold that can almost approach the reach. In other words, the biggest tube I could get before this becomes an ill-posed problem. Okay. So that's the idea. So what can we say here, right? So what we can say is actually, it's useful, it's interesting, it's unsurprising. What we can say is that if you have data and you assume that your function can be written as a function composed with this projection onto a low dimensional manifold, and we make some assumptions about G and we make some assumptions about that manifold, then we can find a rectified linear unit network where the complexity scales with the intrinsic dimension of this manifold. Manifold defined by the function. Okay, so again, what's the nice part about this? The nice part is that the dimension k here may be smaller than even the intrinsic dimension of the data. Okay, and if you think about it this sort, and by the way, that's for pointwise norm on the tube around that manifold. Okay, so my data might be truly capital D dimensional, and I assume that my manifold is just some line in capital D dimensions. I could always build a tube so that the unit square is in this tube. And we'd be able to say that the complexity of the network you need to learn that function would only depend on the one-dimensional object. Okay, and I mean, this kind of makes sense, right? We're reducing the class of how complicated our functions are. we're saying our functions could actually be quite simple. And for simple functions, we're saying you don't need a lot of complexity, right? Maybe nothing too surprising there. And just as a couple of quick comments, log linear dependence on the ambient dimension. All of the constants of this problem worsen as our tube approaches the reach. In fact, if we actually tried to approximate all the way out to our reach, this would blow up, because we would be getting asymptotically close to a point that does not have a unique function value. So that's about the best you can do, right? And I should also note, I know Xiyun Chang, a good friend of mine and colleague, gave a talk here last winter, and she spoke about a paper we worked on where we were also talking about off-manifold learning for neural networks. I should say this sort of extends that theory, because in that, what we were assuming was an off-manifold noise model that decayed exponentially and had to decay quite quickly. Here, we have no assumption about how the data looks off the manifold. We just assume it has to lie inside this tube. Okay. So we're able to get all the way up, approaching the reach, whereas in my paper with Xu, we could sort of only go up to the radius of the partition. Okay. So this is sort of one of the main results that we have. And I want to just give a sketch of how this works, and it's sort of unsurprising. It basically says, if you have a manifold, very low dimensional object, we want to build a partition of unity on it. That's fine. You can do that by building some charts that cover your manifold. And then, and we'll build the partition of unity eta sub I, right? And then the function can be written as the approximation on this little region multiplied by the partition of unity, summed across everything. That's all fine and good, right? The problem is, how do you deal with the fact that this ball, this UI, is still in high dimension? It's still ambient, right? And it's an ellipse. It's not even a circle, right? How do we get that elliptical nature while still having our complexity of our network scale with, in this case, k equals 1? Okay, and so what the real crux of a lot of this comes down to is the following result, which is actually building very particular partitions of unity in this manifold plus noise model, or this manifold plus group action we want to be invariant to model. Okay, and how we do it is actually quite straightforward. We basically define a partition of unity to be a rectified linear unit of 1 minus, and you work on the manifold with, this is basically the projection of x minus zi onto the tangent plane, which like over here would be ti, right? And you're allowed to have one scale on the manifold. And then you're working in the ambient space and allowed to have a different scale off the manifold. And it winds up that when you do these two things together, what you can get is basically the intersection of the ball in the Euclidean space plus a small ball in the tangent space, which gives you exactly this dark gray area. And so basically what we're going to be able to build for our UIs, our charts around our manifold, are going to be able to extend off quite far in the normal direction, while still being thin enough in the tangent direction to be able to pick up the complexities and subtleties of our function. Okay. And that's basically the crux of the idea. We established some nice things about this. How many network, how complicated of a network do you need here? And then everything else just kind of falls out from some 10 pages of technical nonsense, right? So this is sort of what we get, right? Which is pretty nice. It basically says that as long as you're assuming your function really just depends on this low dimensional object, all of the complexity of your network you need should really only scale with that low dimensional object, independent of how far your data can stretch off that low dimensional object and how it stretches off that low dimensional object. Okay. So it's sort of distributionally independent in the normal direction. So that's one model that I find to be quite sort of nice in this perspective. There's another one that I want to talk about as well, which is that first was about regression. What about if we were interested in classification? So we can define a classification model. It's a very simple classification model. My model is going to be, I define, if I have a point X, I define its class by looking at the minimum distance to a bunch of centroids in one class and the minimum distance to a bunch of centroids in another class. And then I just classify X as being which one of these is better or smaller, right? So if it's closer to some centroid from C1, I call it C1. If it's closer to some centroid from C2, I call it C2. And you can generalize this to arbitrary, number of classes by basically saying that I'm going to define a function, which is really a function of the minimum distance to a centroid from some class. Okay, so this set, things like k-means, class clustering or something like that could fall into this model, right? You have some centroids. You're just saying that you belong to the cluster of the centroid you're closest to, and that's the class label you inherit. We can do more things as well. There are functions that scale with distance, but classification falls into this. Okay? But it winds up that what we can get is actually a quite similar result, which is pretty nice. And that basically says, let's assume we have all of these little sets, right? But maybe a lot of them have the same labels or some, maybe they have different labels, maybe they have the same labels. And I'm going to say that those sets are what I'm going to call morally k-dimensional, where you'd need a delta net to build a delta net on that little class. You would need delta to the minus k points. So for example, here, if my model truly was that these three centroids define, well, these five centroids define class 1 and these three centroids define class 2, then I'd actually be in the k equals 0 case. Because I'm just measuring distance to points, and points are 0 dimensional. Right? And I would have m being 1, 2, 3, 4, 5, 6, 7, 8, right? And of 0 dimensional, right? But you could instead have considered distance to a line, distance to a plane, stuff like that. And then the function on that distance is Halder, blah, blah, blah. Then there exists a rectified linear unit, again, that's going to get the correct labeling at a rate that depends on that sort of morally k-dimensional object. So what does this mean? Again, we're assuming a type of invariance, right? We're assuming that our function doesn't depend on all the d-dimensional objects. It doesn't depend on a low-dimensional manifold. All it depends on is its distance to this super, super, super low-dimensional object. Okay? In that case, the complexity just scales with sort of how complicated our classes are. So for example, if k equals 0, if I have just two clusters, and I'm just saying I classify a new point based off of how close it is to either this centroid or this centroid, that's the k equals 0 case. K equals 1 case is how close is it to this line or this line. In that case, the complexity of the network only has to be univariate. That's about the best you can do, right? Your network doesn't have to be large at all. Doesn't need many parameters. And I should also note that I was defining everything in terms of distance, in terms of two distance, but this actually generalizes to other distances as well. And all of the approaches are the exact same. They all involve these partitions of unity, shaping the partitions of unity to go normal to these classes, and then saying anything that gets projected down is, gets that label, basically. So that's the, sort of idea behind this first paper. And here's sort of a summary slide of this. Just to say that you can have data that's truly d-dimensional, and that means you need capital D in the exponent for parameters. You could have manifold. These were pre-known things, then it scales with k. You could have a noisy manifold, or manifold plus a bunch of group actions that you want to be invariant to. And this only scales with k. And then you could even be in this case where you're basically saying that you assume your classes are just written down as distance to some low dimensional set. And then you really just scale with the dimension of that set. And here's I told you that all the empirical risk minimization mean square error results fall out from it. If n is the number of points, this is how many points, this is what your mean square error is going to be as a function of the number of points. Empirical risk minimization. That doesn't mean I'm going to find it when I train a neural network, but it means I could find it when I train a neural network, right? So it's slightly different. But this is basically, this is your estimation error, right? You have approximation of error up here is epsilon, your estimation error is here. And we're getting that it really does depend just on the intrinsic dimension that you think is relevant to your function, which again could be even better than the intrinsic dimension of the data itself. Okay. So that's the stuff about neural networks. Okay. So I'm going to pause for a second. First, I'll see if anybody had any questions. I don't know. If there are any questions on that, please let me know.
Yeah, Alex, can I ask maybe one question? So when you mentioned this project to the lower dimension manifold, and so in practice, do you have a sort of specific choice of guidance of how to choose this low dimension, or just I understand this maybe is a purely theoretic perspective.
At the moment, it's a theoretical perspective. Our algorithm, if you knew the manifold, our algorithm is then constructive. But yes, if I just have a function, I don't have an algorithm for necessarily identifying the manifold, other than the fact that, you know, if we use our construction with some random points around the data and get really good error, we could assume that those points lied on the manifold or something. No, but there's definitely a lot to be done in terms of making it a little bit more constructive. This is just talking about the approximation aspect.
I see. That's cool. So
Yeah.
the other thing, if I may, so because you mentioned the after projection, the function should be invariant under a certain group action, right?
Yeah.
So do you assume your group action is discretized or continuous?
I honestly, at the moment, have not really gone into anything that's hyper-specific about that group action. It's just if it can be written as a function of projection onto a manifold. So in this case, you could say like there are ways to define, you know, like if let's say it was a circle, you know, like a rotation or something like that, and your manifold is just the line that is one orientation of your image. Then as long as you have a unique way to project onto that line, you're good.
Because I'm thinking if you have the projection on the k-dimension manifold, then you ask a group action invariant, which may reduce the dimension even more. Is that my
thought was that the k was after you assume
after the quotient.
Yeah, after you quotient out the group.
Okay.
Yeah, exactly.
Okay.
And by the way, I should note, this is very new work. A student of mine, Scott Mahan, is actually working on this right now, working on building group invariant neural networks.
Okay.
So what if you want to, and in this case, it is a discrete group action. So say, what if you want to be invariant to D8, right?
Discretized.
Yeah. And so then what we're working on then is then basically how the approximation theory carries over to that very, very specific context, but also how to implement that in practice. So he's working on that with just as a quick ad for some friends, some people at Pacific Northwest National Lab, specifically a guy named Tim Doster, who's a friend of mine from grad school. They've been working on that, and I'm working with Scott as well. He's a student that I advise, and so we're sort of moving in that direction.
I say, cool. Thanks.
Yep. Okay. Cool. So, like I said, I'm going to move on to a new topic for a minute. I want to talk about invariances again. So what I want you to do, take a second, sort of shake it off, right? We're not talking about neural networks anymore, all right? We're going to be talking about distributions. And what I want to talk about briefly, so by the way, I realized I forgot to include one slide. I'm just going to come back to refresh should have left this slide here. Just going to come back to just refresh your mind of what the question is. Say I have some distributions, density, PDFs, something like that. And depending on how it looks, it gets a class label. So if it's a Gaussian, it's labeled 1. And if it's a uniform, it's labeled -1. Okay. And I want to do a lot of things. One, I want to talk about how to do learning on this. But two, I want to talk about how to be invariant to group actions such as shifting the Gaussian or rescaling the Gaussian. Okay. And how to build those invariances into learning a parametric function so that I don't have to have that many parameters in my parametric function. Okay, so that's the framework, the idea. I didn't have that as the next slide. So let's talk about it. And as a quick refresher or quick idea, I want to talk about a very, very natural distance between probability distributions. And that is optimal transport, or Wasserstein 2. Okay. So what is this? If you've never seen optimal transport before, 1 second crash course. Say I have two distributions, mu and nu. I can define the optimal transport between them by saying, all right, what is a map? So if T is in this set of couplings, if it's what's called measure preserving. In other words, if it's the analogy of piles of sand. I want to learn a mapping T that takes a piece of sand from this pile and puts it in the hole over here. And I want to do this, any T that takes a point, drops it in, takes a point, drops it in, and winds up moving this pile to that pile. That is a map. Optimal transport is finding the map that takes the minimum work to do that. Okay, so basically, I could have some really weird way to prescribe where the pieces of sand moved, or I could have just had a very simple thing, which is just kind of push all the pieces of sand forward equivalently. Those might involve different amounts of work. The one that attains the smallest work, and by the way, when I say work, I mean physics, like physical context work, force times time, or force times distance. The one that attains the minimum, that's called the transport plan, and the distance, which is this integral, is the Wasserstein distance between the two distributions. Okay, so there's a lot of benefits about it. It's a very natural idea between probability distributions. It scales correctly with shifts and scalings and rotations. It doesn't have what's called saturation. If you move a distribution really far away, the distance increases still. There's a lot of cons to it. It's really expensive to compute, requires some sort of linear or combinatorial optimization. Another problem would be, what if I had a bunch of different distributions and I wanted to talk about all pairwise distances between them? Then I'd have to do n choose 2 Wasserstein distances. One of them is expensive. N choose 2 is impossible. Okay? And I should note, this doesn't actually inherently generate a embedding in which we can do any sort of parametric learning. This is just a distance. Okay? So I want to sort of go in the opposite direction this time. I want to propose a solution and then talk about what we can say about this solution. Okay? And I'm doing it this way because this is actually work that existed prior to my interest in this. So there's this guy, Gustavo Rode, who's been driving this for the last few years. He's done some really interesting work. He said the following. I'm going to define what I call the linearized optimal transformation. So here's what that is. I take a distribution mu, say this uniform distribution, and I learn the optimal transport to a fixed Gaussian here in the center. So that is a function in L2. It is pushing this blob to look like this blob. Okay, and in an optimally efficient way. Here's what I'm going to do. I'm going to say that that transport map, that function, is a feature of the red blob. So I am actually going to change my representation of my distribution. And instead of working with mu, which is this kind of nebulous object in a probability density space, I am going to represent mu by the function that maps mu to sigma. Well, maps sigma to mu. Sorry, did it backwards. The adjoint of that map. So I'm going to define it by the function that maps sigma to mu. That is my feature set. And that's what we're going to call the LOT embedding. Because I am embedding probability distributions into the space of L2 functions. Okay? And here, we can talk about learning. Because now, I am in L2 space. So what if I build a classifier in L2 space that goes from the transport, takes in a transport plan and spits out a class label? Is there something about the transport plan from the red blob to the Gaussian that is uniquely different than the transport from the blue blob to the Gaussian? Okay. And similarly, we can define distances here. And there are a lot of questions. What do we need to know about this embedding? What are natural actions that will be efficiently learnable? So this is the invariance part. What am I going to know about this space so that I can figure out what types of functions are easy to learn and what types of classifiers are easy to learn and what types of classifiers are hard to learn? Okay. And I should note Gustavo and Akram Al-Drubi and a student of theirs, I believe, actually put out a literally concurrent pub with us putting this out. We put them out on the archive on the same week. Doing similar work, we take different perspective, different theory, different scope, but I just want to always shout that out. So anyways, all right. I want to talk about what's called a compatible transformation, because these are going to be the nice group actions that we can be invariant to. So I want to find a group of a family of group actions that interact nicely with optimal transport. So what I mean by that is if I have sigma and I create the optimal map from sigma to mu, and then I apply my group action and push it again, it's pretty easy to show that that's just what S does to mu. The question is this the optimal map? So in other words, if you think about this commutivity diagram, I go from sigma to mu in an optimal way, and then I go from mu to S push mu, which is like shifting mu or scaling mu or something like that. And there's another way that I could have gone directly from sigma to S push mu with the optimal map. The question is, when are these two things equal to each other? Because if I can find S's where they are equal to each other, life becomes very, very easy. Okay? And by the way, the reason you have to do optimal is because if you don't choose optimal, there's sort of an ill-posedness problem. There would be a ton of different maps that are very far apart from each other in L2 space, and you'd have no way of knowing how to choose the quote-unquote correct one. So the fact that we're using optimal transport instead of just picking a transport is basically like a way to make this problem well posed. Okay. So I want to talk about what a compatible transformation is. It's basically what I just said. I want to find a family of actions, group actions, that if I were to do it to mu and then build this LOT embedding, it would be the same as building the LOT embedding and then doing the group action. Okay. So I won't go in, we could go into details. I'm a little out of time, so I'm not going to go into too many details, but I'm going to give you some examples. So shifting a distribution satisfies this compatibility assumption. Scaling a distribution satisfies it. Affine transformations satisfy it. Here's the beauty of it. If I take a convex set of these compatible transformations, then my LOT embeddings of all of those things pushing mu is also a convex set. In other words, if I have mu and I take a convex set of shifts of mu, when I do this LOT thing, it's also going to be a convex set. Convexity goes to convexity. Also, this is one of the contributions that we in particular are making that wasn't in the Gustavo and Akram paper. We define what's called an almost compatible transformation. What if these things don't commute, but they kind of commute? Like they don't get the exact same thing, but the error is small. Example, what if I perturb? What if I have a mu and I just kind of shake it up a little bit? Right? Or I perturb an affine transformation. Well, then we have almost convexity, which basically says that if you have something that's delta compatible and convex, then in LOT space, it's two delta convex. 2 delta convex just basically means there's a little tube around the convex set. Okay. So what this means is convexity goes to convexity. All right. So I'm going to skip over this for now. This is actually about how you would show that things satisfy, that shifts, scalings, affine transformations, all of that stuff satisfy those conditions. It has to do with, I won't go into it now. But my point is that what we now have is a family of group actions that behave nicely with LOT. I can shift a distribution, I can rescale a distribution, I can perform an affine transformation of a distribution, and I can perturb a distribution. And a perturbation is basically any almost affine transformation. So a shift in a scaling, it's a change such that there's a shift in a scaling that is almost the same. And that is going to be what I'm going to basically call like my equivalence class of mu. All those actions applied to mu will wind up being a convex set. Okay. So why is that nice? Let's say I have a binary classification problem. I'm going to make some assumptions. I won't get into the assumptions at the moment, but let's say I have these things that are delta compatible, shifts, scalings, affine transformations. And sometimes I'm doing them to mu, a Gaussian. And sometimes I'm doing them to nu, the uniform distribution. Again, I'm just picking these as examples. It could be anything, right? Well, if the set of group actions was convex, then all those group actions applied to mu is convex. All those group actions applied to nu is convex. And it's actually pretty easy to show, we're going to make an assumption. That assumption is the minimal separation between these things is 6 delta. Basically, there's no way I can shift mu and get nu. There's no way I can rescale mu and get nu. They have to be disjoint and also a little bit apart. Okay, if they weren't, this isn't a well-posed problem. If that's the case, this is a convex set, this is a convex set. And thus, by Hahn-Banach theorem, those two sets are linearly separable. Okay, and I should note, when we're working very, very specifically with shifts, scalings, affine transformations, and perturbations, we have exact results about what delta has to be for this Wasserstein distance so that all of these things work out nicely. Okay, and they're related to sort of how far away is mu from sigma, blah, blah, blah. I won't go into all of the conditions. These are not perfect bounds. We want to make these better. But the point is that if you have some group actions to mu and some group actions to nu, when you embed them into LOT space, you're going to have two separate convex sets, which means you can draw a linear separator between them. And just as a note, this distance in LOT space is an almost isometry with respect to shift, scalings, and affine transformations. It's Hölder 1/2 continuous. Basically, if you take any district, this is just sort of almost a byproduct of what we wound up proving. But basically, if you take any shift, scaling, affine transformation, or perturbation of mu and another one and look at their transport plans and compare that to the actual Wasserstein distance, that difference is Hölder 1/2 continuous, where the epsilon is related to how much perturbation you're allowing. So in particular, if you're only shifting and scaling in affine transformations, this is an isometry. Okay. And it winds up working out in practice as well. But I want to talk about the learning part. So give me like, I got like 2 minutes, I think. I can finish this up. So how does this matter for the invariance, building in invariances for a learner? Our classification model is that this target function I want to learn is that I want to be invariant to all of the h's in this set: shift, scalings, affine transformations, and perturbations. Well, if that's the case, then when I embed all of my objects from mu, I get a cluster. And when I embed all my objects from nu, I get a cluster. And they're convex and they're linearly separable, which means I only need to build a linear classifier. Linear SVM will do the trick to separate these very, very, very complicated objects. This doesn't look anything like it has a linear separator, but in the space that I've described, there's a linear separator. And I should note, in practice, technically L2 is infinite dimensional, so what you do is you project all of these distributions onto some grid, and then the number of parameters you need just scales with the grid size. Okay. So I want to show an example of where this is interesting. Pick a really, really basic example, but I'm going to mess around with it a little bit. I'm going to pick a bunch of 1s and a bunch of 2s. And I'm going to think about these images as being densities on R2, right? A 1 basically comes up, comes down, and normalize it to be norm 1, right? So it's a density on R2. So I'm going to sample a bunch of MNIST images from 1s and a bunch of MNIST images from 2s. And then I'm going to make it harder. I'm going to rescale my image by doing a random shift and random resizing of the 1 and of the 2. So now my problem is I don't just have a 1 and a 2. I have a 1 up in the top right-hand corner that's really tiny, and a 2 in the bottom right-hand corner that's really, really big, and another 2 over here that's smaller. And like there's all these affine transformations. And then I do a little bit of like rotations to them. That's the perturbation. So what I'm going to do is each one of those, I'm going to use LOT, and I'm just going to do the optimal transport between that density and a Gaussian centered in the center of the square. Okay? And that is my feature space. And now what I want to do is build a linear classifier in that space. And this is a plot of the testing error as a function of the number of training points that I need. So we've made the problem harder because we're not even centering the 1s and the 2s. They're all over the place. And yet, if we have 60 examples, we'll have a test error of about 5%, test accuracy of 95% on this harder problem. If we get up to 100 examples of each, you're basically doing as well as a neural network would do. And again, this is on the weirder problem where you're rescaling these things. So you don't just have like a uniform filter everywhere. You have to deal with filters of a bunch of different resolutions. And also, this is the LDA embedding of these test sets. Oh, sorry, and I should have said, this is what happens if you reduce it using PCA to the same dimension. It fails. You can't build a linear classifier in PCA space, but you can in LT space. This is an embedding into 2 dimensions of the PCA. This is an embedding into 2 dimensions of the LOT. You see that it does in fact have a nice linear classifier. So that's basically it. There's a lot of current directions I'm going with this. What if we want to reduce the complexity? You still have to compute optimal transports. So we're moving towards fast, approximate optimal transport algorithms. What happens if you go beyond epsilon perturbations? What happens if you don't just assume sigma is a Gaussian, but allow it to be like a barycenter or something like that? This is ongoing work. So yeah, these are a couple of examples that I've been working on recently where building in these invariances really, really does help you build low complexity classifiers. So with that, that's about it. Questions?
Thanks, Alex. This is a very cool talk. Any questions so far? Question? I do have a couple of questions in terms of the second part. Well, I have other questions in terms of the first part, but we can talk offline. So, so in this picture, right? So, like, how many basically how many images do you use when you?
So the x-axis, so basically 60 examples of a 1 and a 2.
I see.
But they're these weird perturbed ones. And then this is the test accuracy on 100 digits from a testing set.
But the blue curve you have is also, you're also using PCA or use something else?
No, sorry. The red curve is PC. No. This is directly in the LOT space.
Yeah, but you use PCA in the LOT space?
No.
But then how do you get the classification result? You use some classifier? What kind of classifier?
Well, yeah, we just build a linear classifier. Basically, I should have said, because these images are on a grid, LOT space is not really L2. It's actually like R784.
Sure.
And so we build a linear classifier in that space.
I see. So one is the linear classifier. The other one is just PCA on the original space.
PCA and then a linear classifier in PCA space.
Okay, I see. I see. I see.
Yeah, the point here is to say not all dimension reductions are built the same.
I see. You use PCA as a dimension reduction, and you use the same. So the message is use the same classifier applied to different feature space.
Yeah. And by the way, I should note, if you don't have shifts and scalings of your image, PCA can actually do a lot better because you're sort of dealing with everything centered. Yeah. But if you don't have that and you were dealing with images, like natural images, you don't have everything centered in the center of the image, right? And so when you get rid of that, PCA absolutely breaks down, right? And there is some literature that says that neural networks don't do great in that either, right? Neural networks kind of implicitly assume that you have that nice image net, everything's in the center, you know? And so this is basically saying that like, we really don't need that assumption at all to be able to build nice classifiers. And again, linear classifiers. Okay.
This is cool. So I have a question in terms of this LOT embedding, right?
Yeah.
So the big thing is, the advantage, the huge advantage, as you mentioned, is that this is a rotation, translation, scaling invariant. Therefore, you can sort of automatically caution those ambiguities that give you better results. But to me, it seems to me that the big challenge is the computation cost, right? You every single image you have to match with a reference image. You compute that.
Yeah.
Is that could slow down the whole thing, right? So
I 100% agree with you. Yes. So what we're working on now is, and Caroline's actually almost done with this. She's been really driving the research on this, I should say. So Caroline is finishing up the equivalent theory for this in sinkhorn iterations. So sinkhorn is an approximate Earth mover distance algorithm, right?
Depends on how big of the entropy term you are choosing, right?
And we can actually talk about how this breaks down with the entropy parameter. Yeah.
I see.
That'll hopefully be out in the next couple of months.
I see. But how does this compare with because even for the MNIST data, right? They have a 70K images. You compare this, I don't know how much time do you need, even use a sinkhorn. But how does this compare with like people develop this rotation translation invariant feature, like Stephen Malag? He has this.
Yes,
stuff.
I totally agree with you. So definitely, it's going to be more computationally expensive, no question. But
it's very elegant, I would say.
Yeah, but I want to emphasize I'm using images here, but there is nothing about images that is specific. So in fact, one thing that we have been looking at is there's a medical test called flow cytometry. So I've worked on this in other two-sample testing problems in the past, but flow cytometry is basically this problem where you take someone's blood and you treat it with chemicals and you drip each cell through a thing, and it gets a representation in 9 dimensions. So a person is like a point cloud in 9 dimensions. Right?
I see.
Well, now the point clouds are very, very irregular. They are bizarre looking, right?
Sure.
I mean, and like what differentiates having leukemia from being healthy is like a very weird, set of transformations.
Okay.
So there, you're now just dealing with point clouds in 9 dimensions. It would be hard to build like a scattering transform or something like that. But if we just think of those as being samples from a distribution, we can still do the exact same thing. What would be the map from that point cloud to the 9-dimensional Gaussian? That is our feature set, and then build a classifier on it. So this is a lot more general than images, but images is just like one example.
I see. That's interesting. So in the point cloud setup, you view each point cloud as a delta distribution, and you sum up as a distribution in the 9-dimensional space. Is that what you mean?
Yeah. You can either view it as a delta distribution, or you can project it onto a grid, and then view the grid, and then do optimal transport on the grid.
But will this automatically rotation invariant? Because you have a point cloud, you rotate it in a different location of the space. Well, this will give you a very different distribution.
Well, so all right. So one comment. So it's not necessarily rotation. It's the shift scaling affine. The rotation winds up actually being classified under the perturbation. So you can do like small rotations.
Okay, I see.
But yeah. I know what you mean. Yeah, it would be how you define the rotation, right? It would sort of be that you'd want to have the like a small perturbation rotation would be a small rotation centered around the mean of the distribution.
I see.
Right? So that's why it falls under the perturbation term.
I see.
But shifts and scalings are good.
Okay. I got what you mean, and that's very interesting. Yeah. Thanks.
Yeah. I honestly, I have not worked on optimal transport until this problem. I've worked a lot on statistical distances and some statistics between distributions and stuff. But honestly, I feel like this view of the fact that optimal transport gives you a lot of linearities, there's sort of a lot of meat on the bone. And right now it's basically Caroline and I and Gustavo and Akram that are thinking about it. So I feel like there's really a lot of sort of interesting places to go with this.
Yeah, I agree. Because when you mentioned this rotation invariant, we used this optimal transport before to do point cloud registration, and basically we use it in the eigenspace and figure out the rotation in the eigenspace because there's a there. Then we do some. We need to put some rotation group there to make it rotation invariant. Otherwise, it's not exactly rotation invariant.
Yeah. So you'd have a little bit of trouble building a full rotation invariance out of this. But this is actually something we're starting to look at now. We actually think that this is because the reference distribution, we're not making any assumption about it. And in particular, it would be fine if it was isotropic, like a Gaussian. So we're actually starting to think about also, what if you don't just have one reference distribution, but several at different rotations? Then you actually can pick up rotation information. Right? So obviously that makes it more complicated algorithmically. There's a lot of stuff to push through.
Yeah, I got it. Yeah, thanks. Very nice, very interesting. Any more questions? If no more questions, let's thank Alex again for this very, very nice, interesting talk. Thanks so much, Alex.
Awesome.
So I'll definitely. So let me stop recording.